Now the topic is image sensing and acquisition. So that means here how we just sense an image and how we can acquire an image by using that sensors, right? So here the types of images in which we are interested are generated by the combination of an illumination source and the reflection or absorption of energy from that source by the elements of the scene being imaged. As I said earlier in the light and EM spectrum topic, what is that here? So the particular based on the illumination source like a sun, light, anything, some other illumination sources are also there. We will discuss that one later. So now under that illumination source, right? So based on the object, that object absorbs a particular light energy and then gives some light signal that is reflected back from that object. Based on that, what is that? A reflected light signal wavelength. We will see one color. Our human eye perceives some colors in the visible spectrum, right? So here that means the type of images in which we are interested are generated by the combination of an illumination source and the reflection or absorption of the energy from that source by the elements of the scene being imaged. Three principal sensor arrangements are used to transform illumination energy into digital images. Now here we should develop what is that the light signal into the what is that electrical signal to generate the images, right? So that means here we should convert light energy into the electrical energy. So we should use some sensors here. So here those sensors arrangement, based on that sensor arrangement, we have the three different what is that sensor arrangements, right? So three different sensors are there. So here one is nothing but point sensor, another one line sensor, another one array sensor. Based on the sensor arrangements, right? If you use one sensor, one sensor, that is said to be point sensor. If you use the sensors in one line, it may be either vertical or horizontal, that is said to be here line sensor. Suppose so many sensors are arranged in to what is that m by n manner or array manner, then that is said to be here array sensor, right? So now here these sensor arrangements are used to transform illumination energy or light energy into the what is that electrical signals, that is nothing but our image, right? So firstly that is analog image. Next it is converted into the digital image by using sampling and quantization. Right now, the idea is simple here. What is that? Incoming energy is transformed into a voltage by the combination of input electrical power and sensor material that is responsive to the particular type of energy being detected. So, based on the what is that input electrical power and sensor material, we just here transform the incoming light energy into the electrical signal or voltage signal, right? So now the output voltage waveform is the response of the sensor and a digital quantity is obtained from each sensor by digitizing its response, right? See here, these are the three different sensors, right? The first one is a single sensor, next one line sensor, next one array sensors, right? So see here, this is the single sensor. The arrangement, the whole arrangement is appeared here. What is that? The single sensor, this is a sensing element. So output is nothing but voltage waveform. So input is here light energy and some it needs some additional power, right? So that's why here input power. So this sensor is enclosed by certain arrangement. So that is nothing but housing here. Now here here we are using one filter. So here filter, from the filter only the light energy is passing, then passing, and then the sensor converts the light energy into the, what is that, electrical signal, that to voltage waveform, right? So this is the story behind the single sensor. So each sensor principal operation is is as in the same way. Now here, now we if you take this type of sensors, right, in inline, right, like this, right, in one line, so that is said to be line sensor. So now if you take same sensor like in this manner, that is said to be here array sensor, right? Now how many sensor arrangements are there here to transform light energy into the electrical signal or some image? So here, that is we have three things. One is the single sensor, line sensor, array sensor, right? So now here, say this, the first one, what is that, single sensor. So single sensor means, right, so how we generate one image by using one single sensor, right? Say this arrangement here. So to generate the 2D image, 2D image, you know that what is 2D image? 2D image, that means two dimensional. So we need the information along the x direction and of course along the y direction to generate that type of 2D image. So with one single sensor, how we develop this 2D image, right? That is interesting here. So see here, this is the arrangement here. So now one drum is there, right? So that here the film is placed here. What is the use of film? We will see, right? The one film is there, and then this is rotating like this. There is a mechanical arrangement to rotate this drum like in this direction. Now here see this one screw arrangement is there. So here we are placing one sensor. So this is always moving from this side to this side. So that means that this is under the linear motion, right? So that means here one film is there. See this? So now here the sensor is moving from this direction to this direction. So here sensor actually reads the particular light signal value and then converts that light signal into the electrical signal, and then so give the appropriate value here on the film. Now now first initially the mechanical drum is in the stationary mode. So that means here firstly, so place this sensor here. So here on the film we have placed one electrical signal value, right? So based on the sensor input light energy. Now here the sensor is moving linearly along this direction. So now move this one to this place, right? So now here is uh, what is that, we just fix the value, how much distance it is moving, like what is the next value, what is the next position of the sensor to read the light energy, right? So predefined values are there. That means a mechanical arrangement will tells you what is that, how much the sensor is, how much distance the sensor is moving, right? So along the linear direction. That means initially if it is at in this position, so placing what is that, mechanical arrangement, placing of that mechanical arrangement, we may take this one within maybe 0.01 centimeters, 0.001 centimeters, like that. So correct. So just an example. Now here after that it reads the electrical signal, and then what is that, it reads the light energy and converts that one into the electrical signal. That value is placing here in this film. Now here in this way this sensor is moving, and then note down all the light energy values. That means converted electrical energy values. Now here after finishing this one, right, So okay, so that means it may take some time maybe to complete this line, maybe some duration is there. So we just give that information to the what is that, this drum. So this drum is moving after finishing the certain time duration, right? So suppose if this sensor takes what is that, the 10 seconds time to complete one line. So after 10 seconds it is moving like this, one step moving, right? So what is that one step here? So that one step may be some distance, right? So here predefined distance. So now at that position it is moving, and now it goes back and then starts again the same activity. What is that? It reads the particular electrical it gives the light energy and converts that one into the electrical energy, like that. Okay, so observe this one. So this is moving this side and this is moving this side. So whole information is here placed on the film. So am I correct? So here it is nothing but it looks like what is that, on a typewriter, a type machine. What is that? Type writing machine. And of course here this is the nothing but arrangement used in high precision scanning actually. So in scanning we may use this technique, high precision scanning. That means this is very cheaper one also, only one sensor is used, that's why inexpensive. So and also we can get the high resolution images. High resolution images means say what is that, linear motion and rotation, those two are actually predefined. So that's why here we may get the high resolution images. But so due to that, but to get the high resolution images, that means the time factor is very important here. So that means here it may take to note down the each and every value, very narrow values here, to get the high resolution images. It may take a lot of time. That's why it is slow one, right? So here slow one. So here we may use what is that, flatbed mechanical arrangement also. So rather than this what is that, circular motion, flatbed mechanical arrangement also there, that is said to be micro densitometers, right? So this is nothing but single sensor arrangement. By using this we can convert light signals into the images, right? So here the most familiar sensor of this type is the photodiode. What is that? Of course, you know that one sensor that converts for light signals into the electrical signal. That is nothing but here photodiode. Here that photodiode converts the light signal into the electrical signal, that is which is constructed of the silicon materials and whose output voltage waveform is proportional to the light. So okay, now here we are using one filter, so in front of the sensor, that improves the selectivity, right? For example, if I use the green filter in front of the light sensor, that means that sensor is favorable to the green band of the color spectrum. So it passes that one, and remaining particular one, those are eliminated. As a consequence, the sensor output will be stronger for green light than for other components in the visible spectrum, right? In order to generate a 2D image using a single sensor, there has to be relative displacement in both the x and y directions between the sensor and the area to be imaged, right? As I said earlier. So this is nothing but, what is that? So to generate the 2D image using a single sensor, there has to be a relative displacement, right? So in both the x direction, that means a linear motion of the sensor, and also y direction, that means what is that, drum rotating, right? So in the anti-clockwise direction, right, between the sensor and the area to be imaged, right? The arrangement shown in the figure is used in high precision scanning, where a film negative is mounted onto a drum whose mechanical rotation provides displacement in one dimension. The single sensor is mounted on a lead screw that provides motion in the perpendicular direction. Since mechanical motion can be controlled with high precision, this method is an inexpensive way to obtain high resolution images, but it is slow, right? Other similar mechanical arrangements use a flat bed with a sensor moving in two linear directions, right? That means here in the previous case we have seen one is the what is that circular motion, another one is a linear motion. So now here we are using two linear directions, linear motions. Now then we can that arrangement is said to be here flat bed arrangement. So here these are called as micro densitometers, right? Now coming to this one, next one, what is that? Line sensors. So line sensors means here at a time on that means so in one line so many sensors are arranged. At a time we can capture the particular light signal, and then otherwise we can convert the light signal into the electrical signal, right? See this, this is the arrangement here. So if suppose this is a sensor strip, so here strip means from this to that end position, so place so many sensors here. So if it is continuous, see here when logic is there, so if the sensor strip, that means continuous nature, that's in sensor strip. So one sensor that is taking like this, okay, so in long one, right, like a scale, right? So here if you take this one, so we can get the what is that, analog signal nature output. Am I correct? Continuous one, analog nature output. If I use the so many individual sensors to fill this sensor strip, that means if I use the 1,000 sensors, right? So for this, so 1,000 individual sensors means automatically it gives the digital value, right? There is no need to again discretize the spatial coordinate. We just take it only gives the what is that, sampling output. Okay, no need to do the sampling again. Okay, am I correct here? So that means here, so based on the sensor strip here, maybe it is a single one, and then looks like a one scale, right? Now you should do the what is that sampling process to convert analog image into the digital image. Otherwise if you use the so many sensors here, right, like 100 like that, automatically sampling processes completed here, right? So okay, now here, so this sensor strip is arranged here, this is moving like this, so linear motion is this one, right? So here one image line out per increment of linear motion, right? After scanning this line, this is the imaged area, after scanning this line, one increment will be what is that, done, then and next line we can scan easily. So this is the story here for the line sensor. And of course the fingerprints, in fingerprints we are using the same technique. And now see this, have you seen this one, right? Right, so okay, here in hospitals we will we may observe this one. So here some what is that here, some arrangement is there, ring arrangement. So this x-ray source is fixed here. So here is a one bed, right? So that one is moving and moving in this direction. So whole body is scanned by using this ring, right? So it's okay. Now here, of course, this one also actually this is in linear motion like this, right? So it is moving like this. Of course, today. This one also rotatable also, so we are available that arrangement also available now, this one also rotatable like this also. So here it's okay. Now this is in linear motion, it is moving like this. Now whole body from the particular head to what is that, so what each part we will scan, right? Okay, now this one is nothing but, this is nothing but linear motion, that means this is moving in this direction. So right, here this one is the illumination source here, it provides the light signal. So here the in this we are using what is that sensor ring is used here in this direction. Sensor ring is here. Now here this sensor ring, what is that? Converts sensor ring is converts light energy into the, what is that, um, electrical signal. Then so here, based on the illumination source that is transmitted from our body, right? So here that one is captured by this sensor ring. So then it converts the light energy into the image. So this is a story here. In medical we are using this type of units, right? Okay, now here, um, which is used in most flatbed scanners. Inline sensors are used in airborne imaging applications. It's okay, right? Now, see this. A geometry that is used much more frequently than single sensors consists of an inline arrangement of sensors in the form of a sensor strip. The strip provides imaging elements in one direction. Motion perpendicular to the strip provides imaging in the other direction. The imaging strip gives one line of an image at a time, and the motion of the strip completes the other dimension of the two-dimensional image. Lenses or other focusing schemes are used to project the area to the scan into the sensors. Sensor strips mounted in a ring configuration are used in medical and industrial imaging to obtain cross-sectional images of 3D objects. A rotating X-ray source provides illumination, and the portion of the sensors opposite the source collect the X-ray energy that pass through the object. This is the basis for medical and industrial CAT, like a computerized axial tomography, right? It's okay. So this is nothing but line sensors, right? So coming to the array sensors, right? So array sensors means at a time, right? So based on the m by n size of an arrays, you can convert the light signal into the image, right? So that means at a time you can capture the image. So this is used in what is that nowadays we are using that technique. This is nothing but Kodak CCD KAF 3200E, right? So on IC, like IC. So here we are using the same technique. So here the pixel size is 6.8 micron square, or 2184 by 1472. What is that image size will be taken by using this particular sensor, right? Okay, now here, see this, an individual sensors are arranged in the form of a 2D array. So here actually we have seen in this, right? See this. So this is the array, right? So m by n size of an array. Suppose here 1 2 3 4 5 6 7 8 9 10 11 12. That means a 12 by 12, 12 by 12 arrays are used here. Okay, right? Now see, so individual sensors are arranged in the form of a 2D array. Numerous electromagnetic and some ultrasonic sensing devices frequently are arranged in an array format. This is also the predominant arrangement found in digital cameras, right? A typical sensor for these cameras is a CCD array, charge coupled device. What is the CCD? Charge coupled device array, which can be manufactured with a broad range of sensing properties and can be packaged in rugged arrays of 4000 by 4000 elements or more, right? CCD sensors are widely used in digital cameras and other light sensing instruments. The response of each sensor is proportional to the integral of the light energy projected onto the surface of the sensor, a property that is used in astronomical and other applications requiring low noise images. Okay, CCDs arrays are there and CMOS arrays are there, right? So actually there is the another topic. Actually we do not have that one actually. What is that? CCD versus CMOS sensors, right? So you will see this one in YouTube. uh, so if I will provide that link also to you, right? So okay, see that how the CCD is working and CMOS sensors are working. Okay, right? So okay, now here next one is the digital image acquisition process. Digital image acquisition process means up to now we have completed image sensing. So by based on the sensors, that means maybe point, line or array sensors, you just sense the particular image, that means a light energy that is converted into the electrical signal. Based on that we just sense one image and then we can get one image, right? So okay, right? So what is the total process here we will discuss here, right? So now see, this is the imaging system. We are arranging here the sensors, right? So okay, so itself consists of the sensors, right? This is the scene element, this is the illumination source, just an example. So take the sun here. So scene element. So now imaging system captures this scene element under the illumination source. So based on this, what is that light energy? So this object absorbs the light and gives some energy, light energy. Some light energy is reflected from this object. Now that this imaging system takes that light energy or a particular reflected signal, then that converts to the electrical signal based on the sensor. So that electrical signal or a voltage waveform, based on that voltages, so we just use the colors here. Okay, right? So this is nothing but the actually here actual output, right? So but here based on the sensor arrangements here, so after digitizing, suppose if it is having the digitized system which will gives the output like this. So otherwise, if you have the information like voltage information at each location, so or for whole system, right? That means it is nothing but a analog image. By using sampling and quantization process, we just convert this analog image, right, internal analog image into the what is that, a digital image, right? So okay, so this is the nothing but digital image acquisition process. See here, the principal manner in which array sensors are used is shown in figure 1. This figure shows the energy from an illumination source being reflected from a scene element, and the energy also could be transmitted through the scene elements. The first function performed by the imaging system shown in figure C is to collect the incoming energy and focus it onto an image plane. If the illumination is light, the front end of the imaging system is a lens which projects the viewed scene onto the lens focal plane, as the figure D shows. The sensor array, which is coincident with the focal plane, produces outputs proportional to the integral of the light received at each sensor. Digital and analog circuitry sweeps these outputs and converts them to a video signal, which is then digitized by another section of the imaging system. The output is a digital image as shown in figure E, right? So here is nothing but A, B, C, D, E. What is the A here? Illumination source. What is B? Scene element. C is the imaging system. D is the focal plane, right? Internal imaging system. Now what is the E here? Output image, right? After some sweep circuits like what is that sampling and quantization process, then you can get this one, right? So that is the here intention of this digital and analog circuitry sweeps. Okay, now this is nothing but what is that image acquisition process. Okay, now coming to the image formation model. What is the image formation model here? So here the images are represented by f of x comma y. Actually, you know that what is that here x comma y are the spatial coordinates, f is the amplitude, and then what is the range of f of x comma y? Right, very important here. Understand this. What is the range of f of x comma y here? When an image is generated from a physical process, its intensity values are proportional to the energy radiated by a physical source. Right. That means, as a consequence, f of x comma y must be non-zero and finite. That means here f of x comma y amplitude ranges actually depends on the what is that light energy intensity. So we don't know the light intensity energy how much it is. That's why it is the non-zero and the finite value. That means f of x comma y should be the 0 to infinite value, right? So here this function f of x comma y may be characterized by the two components. One is the amount of source illumination incident on the scene being viewed, and the second one is the amount of illumination reflected by the objects in the scene. Understand this one? What is that? F of x comma y depends on two things. The first one is here the amount of scene illumination incident on the scene being viewed, right? So that means how illumination source is there, an object that is absorbing the particular light energy, right? So here what is the amount of source illumination, what is the amount of source illumination instant on the object or scene, right? So that is one of the component. Another one is what is that amount of illumination reflected by the objects in the scene. That means that object is reflected the particular signal. So that means the object absorbs some signal and gives some signal, so that is nothing but reflected signal. So the amount of illumination reflected by the objects in the scene, right? That means here the f of x comma y depends on these two, right? So how much energy, light energy is falling on the object, and how much light energy reflected from the object. Okay, right? So this one is nothing but here what is that? One is said to be I of x comma y, another one is said to be r of x comma y. This is I of x comma y, another one is the r of x comma y. One is the illumination, another one is the reflectance. So illumination component is I of x comma y, reflectance component is r of x comma y. So f of x comma y is the product of these two. What is that? I of x comma y into r of x comma y, right? So now here, what is the illumination value here, range? What is the range of illumination? We don't know actually. So that means from 0 to infinite value, right? So 0 to infinite value, there is no fixed value, 0 to infinite. So that's why here I of x comma y range is 0 to infinite. What is the range of reflectance here? Reflectance means here the object absorbs some energy and gives certain value. So that means here if it absorbs a whole energy, it does not give anything, that means zero value. So otherwise if it does not absorb anything, it gives the whole value, that may be considered as a upper value. What is that? 1, right? So we are considering here the an assumption. What is that? If it absorbs the whole energy, there is no reflected signal, that's why it is a 0. If it does not absorb any signal, whatever the what is that illumination source, illumination component is there, so there is a reflectance component, so those two are equal. In such a case, what is the value here? 1, unity, right? So that's why here what is the range of reflectance component? 0 to 1, right? Now here remember that here what is the f of x comma y? I of x comma y into r of x comma y. So here obviously here what is the range of this one here, f of x comma y? So here 0 to infinity is the I value. So and what is the r value? 0 to 1. So f of x comma y range also 0 to infinity obviously. But here we should consider some finite values here, not the infinite values. So here let the intensity of your monochrome image at any pair of coordinates x0 comma y0 be denoted by, so some L is nothing but f of x0 comma y0. Consider like this. L lies in the range. Suppose f of x not comma y0 and just observe the particular value, intensity value at particular location in the image, that is nothing but L. If you observe that L range is L minimum to L max. What is the L minimum and what is the L maximum here? L minimum is it depends on I and R. What is that? I minimum into R minimum is nothing but L minimum. What is the L max here? I maximum into R maximum. So now here, what is the L value, L range? L minimum to L max, I minimum, R minimum to the I maximum into R maximum. So that means here the interval L minimum, L maximum is called the gray value. So if I take the gray image, gray value, right? So here I minimum, R minimum is 0, I maximum, R maximum is obviously infinity. But here in practice, we should take the, what is that value here? Some finite values. That means here maybe it may be appear like, suppose if I take what is that here, for example, if it is a 10 value, I minimum is some value, R minimum is some value 10, I maximum, R maximum is nothing but suppose 150. That means what is the range of this one? 10 to what is that? 150, right? So minimum is 10, no 0 there. Okay, if you observe and observe all points here, L minimum is nothing but what is that? 10. What is the L maximum? At any point, what is that? 150. That means there is no 0 value, 1, 2, 3 value, and there is no 151, 152 values, right? Based on the I and R values, we can get these values 10 to 150 only. The range is 10 to 150. In between, there are so many values, right? In the image. That means here the range is, how can you say the range of a particular image here now? So 10 to 150. That means how can you allocate the number of bits to that particular image? Here in this case it is difficulty in such a case. That's why here, so we just what is that, take the some what is that, uniform values. What is that, like I'm taking like this in common practice, 10 is nothing but 0, 150 is nothing but higher value, right? Like that I'm just normalize these values. That means here common practice is to shift the interval like 0 to L minus 1. So L minimum is 0. 10 means here low, that is a 0. And what is the L maximum here? A higher value, what is that? L minus 1. If I start with a 0, so I just end with the L minus 1, not with the L. So low means 0 means here black, L minus 1 means the white. So all intermediate values are shades of gray, right? So don't consider the infinity values also, and the of course there are no infinity actually, so we can get some value here. We do not get the infinity value here. Since a voltage signal provides certain value here, so we can get the some finite value now. Surely, so here the range is here, to optimize the range here, so the interval is generally L minimum to L maximum. We should consider like that only. But here in practice our comfortable, so to comfortable zone, so here we just take the values from 0 to L minus 1 like that. Okay, right? So okay, 10 to 150 means we may consider like this. What is that? 0 to, so next one, what is that? 255 like that. Okay, in that we just consider 0 to 255, but we just in the image we are having only 10 to 150 only. Okay, right? It's okay. Thank you.